So then in practice, well, once we go through the Illustrative example for the CE sample, I think once you finish all of your synthesis model for your project and then the utility evaluation and all that, when you want to do your attribute disclosure risk evaluation, this will be a go-to place. Okay. All right, so the seed sample synthesis, I only select a few code here to get the thing going. So just refresh your memory, we load the data, we take the log of the income and expenditure, because that will be a better way to fit the simple linear regression model. And then we wrote a JAX code and all that, but in the end, we are synthesizing, in this case, using the example of one synthetic data set, okay? So at the end of the day, we'll have the synthetic one. So this is going back to lecture 405, I think, when we first introduced this. So you can go back to the slides there. And the AR calculation for the CE sample that we're going to do today is m equals to 1, okay, for illustration. You know that when you have multiple, you do it for each synthetic data set and doing the regular thing as before. So the intruder now will know all of the synthesized variables, okay, so urban, rural, race, and expenditure. And the intruder tries to use this information, sorry about my tries typo, tries to use this information to infer the true values of the synthesized variables, income, okay, based on the synthetic data set that is being released, as well as all of the other information that the intruder might know. Okay, so I just rearranged the data a little bit. So in the end, we have the CE data org, which will be the original data with only the 4 variables that we care about. And then the synthetic data, I just make sure that I take the delog it, I guess, get it back to the original scale and then come back to with the same dimension. Okay, so we come, we start with this 2 data sets. Okay, and between the 2 data sets, the first 3 columns are the same because they never changed. Okay, we didn't synthesize that. Oh, not the first 3, but the 3. Yeah, out of the 4, 3 of them are not synthesized. Only the second column, income, is synthesized. So that will be the only difference between the 2 data sets. Okay. All right, so coming back to what we're trying to do, so this equation H, we saw this before, but we put it into the context of the CE, right? So you notice that I took away all of the both faces because the income is a univariate continuous variable. Okay, so now I'm using just scalar, 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 scalar. Okay, but if you have more, you can think about ways to do it. So, so y star is the univariate random variable representing the true the guess. Okay, y star will be one possible guess. Z is the synthetic data, and YUS is the same as before. Okay, but in the context, it will be the 3 columns: the urban, rural, race, and expenditure in the CE sample. All right, so all of this should be fine. And then we're gonna, again, make the same assumption here. We're gonna use the worst case scenario. So our A is y s -5. S is the intruder knows that the synthesis model is based in linear regression. We're gonna assume that. And then we're gonna assume a uniform prior for this. So all of the all of the guesses will be equally likely. So now we're left with this equation 9. That is the one that I was saying that we're gonna have to use the importance sampling to deal with. Okay, so the other, the 3 bullet points here, all of this are about the other parts, right? About A, about S, and then about that prior piece of the estimation process. But now this is the case that we're trying to estimate the probability density of the synthetic data given each possible guess being replaced. Given the true value being replaced by each possible guess. So that's the place where we're gonna have to figure out, well, how to use the F star, and G, and all that. All right, so similarly as before, okay, we already answered the questions, I think, since when Henrik was asking and then also clarifying the understanding, we talked about theta will be, in the CE sample, will be the, I think, theta 0, beta 1, and sigma, okay? And again, they're all estimated on the log scale. So when you're doing all of this, you have to take the log again. So I include that in the upcoming scripts, but in your model for your project as well, make sure that you take the correct transformation. And then, because it depends. I mean, maybe you fit the model on the log scale, but then when you're estimating, like to say your utility measure, for example, you might do it on the original scale and all that. But in this case, especially, I mean, probably only in this case, because we're trying to use the model estimates, the parameter estimates to do some estimation for the attribute disclosure risk, right? So we actually have to go back to how the model was fit, okay? But for the other thing, like utility measure, like all of the measures that we talked about, you should probably just do it on the original scale, right? But then for this one, because we have to use the theta, and the theta is the collection of parameters on the model that we actually fit. So you have to go back to what you're fitting, okay? If you have taken certain transformation of your data, you have to go back to do that, okay? All right, so I repeat the equation for the importance sampling on the top. We're gonna look at it one by one, okay? So different pieces. So H, we know we use this script here to indicate that we're gonna use a capital H number of parameter draws, okay, for the theta. But then the importance sampling is taking the average, okay? Where, as you can think of that, we're doing this part for each H. And then you have capital H number of times of doing this, right? So you do that for each H, and then you take the average in order to get the approximation to the expectation. That's according to the method that we have about importance sampling. So the key here now is, well, how can we make this to work? And so I put the G for you in this case. So our G will be what we're trying to estimate, okay? So that is our G. And the theta, F theta, which is what the earlier slide has, that will be our, I would say, inconvenient or like not convenient or not easily obtained density function, but that is the one that we're trying to estimate with. So this will be our F theta. And then our F star theta is the density that is convenient, which is actually being estimated on the model. Okay? So I think putting all of this together probably gives you a better sense of what we're doing for each piece. Right? If you look at this, we have our G star, that is what we're trying to estimate. So that's the goal. Okay? And then we have the two distribution. One distribution is the actual theta is going to be following from. And then F star is the convenient distribution that we already have draws from. So the theta, the actual theta that we're going to use from the model is coming from equation 13. Okay? So with all of this pieced together, let's come back to the box here. Okay? So what are we doing actually when we're doing the importance sampling strategy here? So we estimate the G function, right, with particular theta, okay? Theta H in this case, right? That's outside. And then we have a ratio, and look at what the ratio is doing. The ratio on the top, when I say ratio, is this whole thing, okay? But the ratio is ratio of ratios, right? So on the top, in the numerator, it is the ratio of estimating theta H under the two distributions, right? It's the target distribution, let's just call it target distribution F, over the convenient distribution. And you, for each H, you can get like a ratio, right? And then the big ratio that we're doing here, you can think of it as normalizing the ratio. Because the big ratio in the end, in the bottom, is doing what? Is getting the ratio for each H and then take the sum, right? And then what this big ratio doing here is normalizing each of the numerator by the sum of all of the possible numerators. So in the end, it's still going to be a ratio. It's going to be between 0 and 1. Okay? And in short, you can think of this as doing that. We want to approximate using, I mean, at the end of the day, it's still like Monte Carlo, we're using multiple draws, right? We're using capital H, number of draws over here, okay? And we know that F star is a convenient distribution. We have draws for them. theta. I should say we have theta. Our theta is coming from here, and it's easy to estimate this distribution. Okay? And we're using them earlier. We said in the slide that we're using them as proposal distributions. So the way that we are making the proposal, as you can see, this is the goal. The G theta H in the end is the goal, right? We're trying to estimate that because that's what's in equation 11. But we're sort of weighting it every time based on its ratio between the F and F star. Okay? Because our goal is about F. We want to get F, but F is hard to get. We have a convenient F star. So importance sampling is a way to help you to estimate. In a way, it's approximation. And to help you get there, it's just like the particular format looks like this. So we have to figure out, as you can see now, what is H, what is G, what is F, and what is F star. Okay. So keep that in mind. I know it might still not be the clearest at the moment, but now we are able to put it into the context of what we're doing. Okay, so remember I was saying GH will be the goal that we're estimating right here. So what that means, if you look at equation 14, yeah, maybe let me just pause here. What do you think equation 14 is doing, and why that is the case? I'm gonna pause. Yeah, the model is Z given, well, it's a bunch of assumption and all that, but essentially we're estimating Z given theta H, right? So Z is the synthetic data. And we know that the only synthesized value for each observation is that Y tilde I. Okay. So essentially what we're doing is estimating Z for each observation yi star. Let me just clear that. For each observation yi star, we're estimating its density under the normal distribution that we fit the model with. Right? So the model was what? The model was yi is normal beta 0 plus beta 1 xi, right? And then sigma. That was the model that we fit. Okay? Now we have what? We have draws of beta 0, beta 1, and sigma. And in particular, because we're estimating the density of Z, and Z is y1 tilde to yn tilde, we're using that as the synthetic value, right? So that's why the key here, as you can see that, is that everything else is just a regular normal density here. Make sure that you're using the synthesized value, the synthetic value that you have in the model to estimate this G theta H. Okay. Xi is the unsynthesized log expenditure. And remember, we only use that as the predictor in the model. If you have other predictors, you just have to factor everything in. Okay. But so this is what our G will be. Okay. So the key here is that because G is looking at the density of the synthetic data given theta. So when you're getting the density for from each of the observation, you have to use the synthetic value in your estimation. Okay. And finally, don't forget, we use the product here because we're assuming each observation are independent from each other, right? When we're fitting the model, remember we write this. Okay. So that's why the joint density will be the product of all of the individuals here. That's why you have a big product I from 1 to n at the front. Okay. So G is about the synthetic data. So G will be the joint density of synthetic data given the draws that you have. So that's why, because each one is a normal. So you will have your yi star, yi tilde here because we're looking at Z even. Okay, we're estimating about Z. The other pieces, it's not about Z, so bear with me. It looks a little bit crazy, but it makes sense in a sense that we are able to use the importance sampling here I'm breaking them into 2 lines just because otherwise it's too long. But this is essentially our G theta. Okay. Okay. And this is the ratio that we saw earlier, right? This will be the F, I think, which one? F theta. Give me a second. I have to take a look before I, okay. So it's F. Yeah, so this part is G theta. This part is F theta divided by, so there's H on each. Let me just get the H here. F star theta H, right? Divided by the sum of H from 1 to capital H, and then the ratio of each of the H here. Okay. So that's why, I mean, the key here, again, everything is about normal density. So that's why you see all of the normal density here. We already saw here, this should be Y tilde I because it's about the synthetic value, because that's what we're estimating theta G theta for. Here, so remember, now we're looking at the target distribution, right? The target distribution that is unknown. So we should use the value from our guess. Okay, that's the target. We don't know. We're trying to approximate, right? And then when we're using the convenient known distribution, we should use the value of yi from the data because that's how we fit the data, fit the model in the first place. Okay, let me repeat that. So we know pH is related to GH, and we already G theta. We already talked about it. However, QH here, we know that should be F, the ratio between F and F star, and then divided by all of the sum because we're doing normalization. Okay? And we know that F is the target distribution that we don't know. And the target distribution is when we're replacing our guess with each possible guesses. Okay? So that's why when you're estimating it, it's about the Y star because Y star is the guess. Okay? That's the one that we're replacing every time. Whereas when you have your convenient distribution, which we know that is fitted on the original data, that will become your yi because that's the actual data that we have in the model. So in short, pH and QH, they look all similar in terms of the density because they're all normal. But the only difference, let me just highlight them using red again. The only difference is what you're fitting here. Okay. And that is because how the importance sampling algorithm was set up in the first place. Okay. All right. So I know we're almost running out of time, so I don't mind if we actually just stop here. I think, yeah, today I try my best to go over the keys. So what's left in this lecture you will see is the actual R code to implement all of this. So I think it's probably a better use of time for you to take a look and also maybe possibly implement it for your project if you want. And then next time when we come back, we're gonna spend, I mean, the first part of that, maybe talking about like finishing the rest of this. And then if you have further questions, especially trying to implement this, either using the CE data or going into your project and do something similar and then you run into issues, we can certainly talk about them and answer those questions. And then we're going to start talking about what we mentioned, differential privacy from last time, from next time. So I'm going to send you like a short write-up for you to read about it, because otherwise I feel like, because that part, that kind of method is also very mathematical. I mean, I try to supplement, as you will see next time, I try to supplement with the code and then trying to see how things are being implemented in practice. But there are certain learning, I think they have to take place as part of your reading instead of just like looking, like participating in the lecture and then might get confused because, well, all of those require certain thinking and then you will have to probably do some derivation yourself as well. So that will be my, I think my end note here. And I will hang out for a few more minutes if you have questions about like your project and all that. But also tomorrow I have office hours, Thursday as well. But I'm gonna like, yeah, feel free to log off because we're running out of time. But I will stay for a few more minutes, and we can yeah. Any other questions? Feel free to email me.